Thanks for coming out, guys. My name's Grunert. I work for Atlassian. I've been working there for about 3.5 years. In that time, I've worked on a number of different products, including JIRA, JIRA Agile, JIRA Capture, and Stash. I've also done some small stuff around Confluence, and I've also done a little bit on Bitbucket, which is actually a Django application. In terms of why I'm here at PyCon, I've actually used to write Python full-time for a company called Rising Sun Pictures in Australia, doing command line tools for stringing together their visual effects pipeline. And I really enjoyed playing board games. So that's me playing Dominion, and that particular picture was used twice in the same day by the Sydney Morning Herald for different articles, which I thought was pretty funny. So what this talk is about is partly about a tool called JMake and the addition that we added around engineering health metrics, which allowed us to measure certain things about our code base doing some static analysis, as well as how we use git-notes to be able to do some interesting storage and introspection over those values over time. So I'll start out with some history. I work on a 12-year-old code base, so I have to be a little bit of a historian at times. So we started out using JIRA as JIRA is built using Maven. So hands up if you've used Maven before. Okay, there's a few people in this room. Now keep your hands up if you actually like Maven. 0 hands, 1 hand, okay. You probably haven't used it as much as us. So Maven has a number of faults, and it will be an entire talk in of itself of me ranting about how much I really dislike Maven. But one of its key faults is just how arcane the command line interface is, as well as how difficult it is to kind of add additional functionality over the top of the command line interface. So we often have new starters start at Atlassian who have never used Maven as a build system before, and they come in to work on JIRA, and they go, okay, I know that JIRA uses Maven to build. Okay, I'll try and use the Maven command line to get some help about how I can build the project. And they'll run Maven -- help, and they'll get this kind of stuff, which is pretty useless, right? It's talking about strict checksums and lax checksums, and nowhere in here, in this first page, does it say how to build, which seems like a pretty key thing for a build tool to tell you. So what ended up happening was a lot of developers kind of started finding these little snippets of Maven and various other bits and pieces that allowed them to get their stuff done, doing, setting versions and releasing stuff and all sorts of that kind of little bits and pieces. And they wrote it in Bash because they're hacking stuff together. So we had this growing bin directory and this growing tool called JMake, which allowed us to wrap Maven with a set of shell scripts to be able to make it easier to understand how to build JIRA and how to get stuff done. But it was written in Bash, and as you know, hopefully, any Bash script that's over about 10 lines becomes increasingly unwieldy and painful to modify and extend and test. So our project began to rewrite JMake in Python. And by doing so, we gained a huge number of benefits. We got testability, maintainability, easy to extend, code reuse. We got excellent command line tools, ability to do these great help strings, all that kind of stuff. So that's kind of the history of how our build system kind of grew over time. Then about a year ago now, we were looking at where JIRA code wants to be in the future, right? So we started to truly document a lot of the kind of layers in the Earth's crust of JIRA. So what ends up happening in a large Java project like JIRA is that people will, over time, discover new and better ways of doing things. So for example, they start out using a Mocky framework like EasyMock, and then somebody goes, oh, Mockito is actually kind of nice. So they'll add a dependency in the POM, they'll pull in Mockito and start to use it in a certain little bit of the code base and test it out and go, oh, that's great. And then they kind of get bored and go on with some other stuff, right? And as a result, you end up with these multiple layers of mocking frameworks being built up and multiple layers of technical debt where people haven't gone through and converted from the old way to the new way. And this is a particularly large problem for something like JIRA because we have 60 plus developers working the product and it's growing every day, and trying to get that tribal knowledge of what the right way of doing things right now is and expand that across the team is actually quite difficult because people will see some existing code that does it one way, say using EasyMock, and then copy that to a new file and write a new test in EasyMock, and suddenly you now have additional work being added to the team who eventually wants to get rid of EasyMock. They just haven't had the chance yet. So we documented it, but we don't really like this document means that somebody has to come along, read it, and internalize all of these little bits and pieces. So ideally, we want something that can encode all these things that we're trying to pay off and run it in our build system and let us know, hey, you're actually making our lives harder right now. So there's a couple of tools in the Java world to do similar sorts of things. So there's FindBugs and CheckStyle, which have some hilariously dated home pages, as you can see. But they're both extremely powerful tools, but they're kind of very heavyweight for the kinds of things that we're trying to measure, right? So for the EasyMock example, for example, if we could just count how many imports to EasyMock there are in the code base and measure that over time and make sure it's not going up, we would get the benefit that we want. But trying to encode that in FindBugs and CheckStyles XML files and build out a large set of metrics like this set here in such a tool is extremely time consuming, so it's not really worth it. So we looked to build our own system to be able to do these simple kind of metrics that we wanted to measure and allow us to run them both on our development machines as well as in CI. And in CI is a particularly interesting problem because we need to make sure that if the number stays the same over time, that's okay. The build can stay green, people aren't making things harder. But if it goes up, we need the build to go red so that people know, hey, you're doing something wrong here and they need to go in and fix things. So I kind of split this talk up into two separate sections. The first is about how we measure those metrics and how we use Python to build this metric pipeline. And then the second part is about the storage and how we store those metrics, the values of those metrics over time and measure whether they go up and down and do some interesting things. So on the measurement front, we have a pretty large code base. So this is in the main JIRA repository. We've got over 11,000 Java files and hundreds of thousands of lines of code. And of course, that's just in the main repository. We have all these libraries and plugins and stuff that contribute code into this code base. So it's extremely large. And we're trying to measure over 50 individual metrics. That's how much we've got at the moment. Ideally, we could expand that to further numbers of metrics. And we need this to be really fast because we would like developers to have the ability to run this locally before pushing the changes up. So here's an example of a run that I did on master this weekend. And you can see it's finished the fast set of metrics in about 18 seconds, which we consider to be pretty good. Usually it takes about 18 seconds for Maven to get out of bed. So in comparison, it's quite good. So how can we do this? So we want to be able to scan these large numbers of files for a large number of metrics and collect these values in a decent amount of time. So a naive approach would be something like this. I don't know if you can see it at the back, but it's just a grep for imports on EasyMock across the Java files in the code base, and we count them. But this takes about 2.5 seconds on my machine. And you can imagine if we did each of these metrics separately as a line like this, it's going to start to blow out into minutes, and that's not ideal. So we would like to be able to do a single pass over the repository, and for each file, execute multiple metrics. So we turn to Python and we turn to JMake to be able to build this system in. So here's an example of the shape of a metrics collector. So we have two main things of note. The first is this once file, which basically allows a metric to opt in to measuring a particular file. In this case, we're only interested in Java files, so we don't end up measuring JSPs or SOI or velocity files or XML files and whatever else we have in the code repository. And the second bit is this onRead line, which gets called back for each line in the file, right? Inside there, we're looking. This is actually the Java package imports one, that the example that I showed you on the previous slide around trying to check for EasyMock imports. We're just looking to see if the line starts with import and the import class that we're looking for is inside the line. And if it is, we record a hit. And at the end here, you can see we're doing something a little bit interesting here. We're saying return not open curly brace in line. And for those people who don't program Java in the audience, Java starts out with a package statement, a series of import statements, and then it's the starting line of the class or the interface. And at the end of that, it's got a curly brace. So we can look at this and be able to bail out of reading this particular file earlier, because we know that after this first curly brace, there's no more import statements. So we can exploit our knowledge of the problem domain by using a tool like this, because we have a little bit more flexibility than you do in Bash. So we can then reuse that Java package imports metrics collector multiple times. And here I've reused it twice to be able to look for EasyMock and mock objects, which are two ancient mocking frameworks, to be able to make sure that over time we're measuring imports into EasyMock and into mock objects, so that we can make sure that people get nudged towards using Mockito. And this kind of reuse is pretty prevalent within the metrics collector. So I think we use the Java package import stuff for 10 or 15 of the metrics, right? So we're getting some great code reuse here across all sorts of different things between, mocking frameworks, but also caching frameworks and all sorts of bits of craft that have accumulated over time, but we haven't had the time to go through and pay back that debt. So here's an example of something a little bit more esoteric and very focused towards our code base. So we have a plugin system which builds jars which nominally look like a regular jar, but it contains this manifest. And inside the manifest, this is an OSGI manifest. And it's got a particular line in that manifest that we need to look for, because with that line, the plugin is significantly faster to start up, and without it, it isn't. So we're trying to make sure that we're getting more people opting into the fast way of starting up over time. So whipping up a simple metric like this for a plugin took an hour, maybe two with tests, whereas in something like Find Bugs or Checkstar, we'll be going for a long period of time trying to get the system to understand how jars work and extracting them and finding this file and looking for the line. So we found it extremely productive for us to be able to measure the metrics using Python. So at the end of that, we end up with a JSON blob that looks something like this. You've got a series of metrics. Inside each metric is the key for the metric. We have a bit of a description so that we can tell developers when they fail the metric, hey, this is what you failed and this is where you can go to get some additional help about how you can make your code better. We've got the current value. We've got the direction that we expect it to be going in, so we can say that for some metrics we actually want to track them going up over time because we're trying to track adoption of something new. And the other last piece of the puzzle is this check thing, which basically hints to the CI system. If it's unchecked, then we don't care if it violates the metric, right? If it goes up and we weren't expecting it, don't fail the build for us. And the reason why we added that is just because for some of the things that we want to track over time, it's extremely noisy. The build becomes very noisy because very simple bug fixes, it's often a lot easier to be able to do things using some of our older systems than it is to migrate an entire file across to a new templating language, for example. So that's the metrics. I'll move into the storage after this. So as I was saying, we have some interesting requirements. We need to be able to run on local developer machines. We also need to run in CI. And we need to know whether or not this value has gone up above our previous expected value. So we kind of wrestled with this for a little bit because we didn't really want to add another dependency into our already kind of complicated CI system. One approach would be to have an external web app or something where you can store these numbers and then pull that data down from that external application, but then we've added another thing that you need to maintain over time and make sure that that service stays up over time and that somebody knows how to maintain it, and that when Fred leaves the company, he passes across the root rights and all that kind of stuff, right? And there's a huge amount of additional stuff that you have to do to get one of those services going and maintained by our IT team or our build engineering team. So instead, we looked to using git-notes. So who saw my lightning talk yesterday? A few people, so not everyone. So I'm just going to quickly go over what git-notes is. So git-notes allows you to add, remove, or read notes attached to objects inside your Git repository without touching the objects themselves, which is pretty interesting, right? Because Git is a content addressable database, and if you change the content, then the hash changes and everything changes, right? This is why it's kind of difficult to be able to change a commit message after you've pushed it up to another repository and someone else has pulled it down. So this allows us to get around that, and that's kind of interesting. This is how it actually works under the hood. So separate to your regular commit graph, we have this second ref pointing at this second commit graph inside our repository. And now very similar to the unpacked format for objects, we have inside this JIRA stats ref, inside this commit, it points at a tree. In the tree, the file name concatenated with the directory name ends up actually pointing at one of these commit objects. So it knows that this particular note is to do with this commit inside the other DAG. And inside that blob, it stores the note, in our case, the metrics. So this is kind of cool, right? We can actually store metric data over time within our Git repository, and we get that data copied across from our, as our repo moves throughout the system, right? So on our developer machines, the data is present. We don't have to pull it from somewhere else. We don't have another dependency in our system. And then in the continuous integration environment, it's there too. So how does this work in practice? How do we hang this together? So in our CI environment on Bamboo, we calculate our metrics using the system that I was talking earlier. We check the baseline by looking at the note, looking up the DAG to find a note for the previous values of the stats. If any of the metrics, any of the individual metrics have increased based on the value that we pulled out of one of the previous commits, then we fail the build. Otherwise, if everything's okay, we store a new baseline. So this is where the storage occurs. We actually only do the storage of metrics into the notes on the CI system. And then locally, we have this kind of workflow. So I can calculate the metrics locally. I can check the baseline just like in CI. But the difference is if it's increased, then I can ask for a reason to be able to add an exception to the rule. And then otherwise, we pat them on the back and say, hey, good job. Make sure you push your stuff. So what does that look like? We've got this here's an output from the EH metric system locally. And you can see right down the bottom here, I don't know if people at the back can see it. It asks, do you want to accept the violations to this metric up the top here in red being increased? And you can say yes or no and provide a message, a reason for the increase. So how we store that is a second set of Git notes. So alongside, we have the JIRA stats that say that it gets pushed in via CI to be able to say this is the value of the metrics at this particular commit. And then we've got the JIRA stats and exclusions to be able to say, okay, I know that this number went up, but that's okay because reason, right? Because I don't know, it's late and I want to get a beer. Might be a reason that a developer pushes in. So how does this work in practice? Do you actually have to know all these arcane Git commands to be able to get it to work? No. Git actually allows you to get the notes out through a simple log command. So you can do git log show notes and say the note namespace that you're interested in. And we actually pull out the notes for the JIRA stats, pull out for the notes for the JIRA exclusion, and do this this calculation to be able to say, okay, have the metrics gone up? Okay, have the metrics gone up and it was excluded by one of the exclusions? Okay, now, you know, yes, good job, or no, fail. So yeah, that's kind of how we do our storage, and by storing it in git-notes and across the entire commit graph, we end up with lots of additional benefits, right? So one example is we have a series of wallboards within Atlassian, which is powered by an open source project called Atlas Board. You can go online and download Atlas Board for yourself and write get a wallboard going that looks like this if you want. But we wrote our own gadget for that wallboard to be able to keep track of some of the metrics that we're interested in over time and be able to visually represent whether or not they've gone up or down. So the only time that you get one of these red ones is if it's if the metric has increased and somebody put in an exclusion, right? So that's how you end up with increases happening. And then we can do these kind of graphs over time of what the metric values are. So here's another example we actually have separate from Atlas Board, but over a set of graphs over time of a set of metrics. So in this case, we're using D3 to be able to manage metrics. But because it's all in git-notes, we've got this full historical data of what the values are over time, which I found to be extremely powerful to be able to build this kind of additional tooling over the top. Whereas other approaches where you would only store, say, the last one, you don't get this kind of benefit. All right, I think that's about all I've got to say about the engineering health metric stuff. Just before we stop for questions, I just want to do a quick plug. So Atlassian is hiring in Sydney, San Francisco, Austin, Manila, Poland, Gdansk, Poland. So if you're interested in working for Atlassian on developer tools in all sorts of different languages, or working on a SaaS platform or infrastructure, or working on a build engineering team, we've got lots of different opportunities at various different skill levels. So if you're interested, either come and talk to me or Roger, who's here in the front row, or have a look on our website, atlassian.com/company/careers. All right, thanks guys.